Okay, I'd say go ahead.
Okay, so it's my pleasure to introduce Hiro Masunaga. So Hiro did his PhD at the University of Tokyo and then did a postdoc and research scientist position at CSU. I believe he overlapped with Tristan Lecoyer in our department. He works on satellite retrievals of precipitation and doing things with interesting things with satellite retrievals of precipitation, everything ranging from looking at water vapor or moisture precipitation, water vapor precipitation relationships he's looked at, to moist static energy budgets, to, I guess, convective organization and comparing to cloud resolving models. So lots of interesting stuff. And then I guess he's going to tell us today about the East Pacific ITCZ, which he's also done some previous work on. So my pleasure to introduce him. Very excited to have him speaking with us today.
Right. Thank you very much, Larissa, for a very nice introduction. And I'm sharing my screen right now. And thank you all for coming to this colloquium despite unusual hour in early morning in your time zone. Actually, by the way, it's 10:30 at night here in Japan. And I wish I could come to Madison to give a talk in person, but as you know, unfortunately, it's still difficult to travel abroad for everyone. So but it's anyway, it's pretty nice to have this opportunity to get together online wherever we are in the world. And thank you for the colloquium organizers for inviting me to give a talk like this. And I'm pretty honored for having this opportunity to give a talk on one of my recent work about the intensification of the ITCZ in the Eastern Pacific. I've been up to this research in the past 1 year or so. In the Pacific ITCZ, particularly the East Pacific, I think I don't have to introduce this ITCZ pattern, which is pretty a nice zonally extensive narrow zone of precipitation and moist air. This particular plot was made from the satellite microwave measurements for the groundwater vapor colored from green to blue, and precipitation from red to yellow. So basically the area of high rate of precipitation agrees pretty well with the area of moist air in the tropics. So this characterizes important property of this Eastern Pacific ITCZ. And the mechanism behind it is typically understood in terms of the Hadley circulation driven by the moist convection in the tropics. And ITCZ corresponds to this area with pretty developed deep convection here, close to the equator. And the ascent inside ITCZ goes to a poleward and eventually goes down in the subtopics. And because of the subsidence, the subtopics is mostly clear sky or kept by the substance, and the area where the cold ocean typically have a stratocumulus class like this. But little attention has been paid to what happens in the middle between the ITCZ and the subtopics. Like here, except for the recent work done by Brian Mipps with co-authors including myself, which is focused on the tropical margins between the moist tropics and the dry subtropics. And these plots are snapshots of the Indian Ocean with the moist and the dry air colored with the blue and orange colors, respectively. These moist topics and dry subtopics are divided by the 48 millimeter contour in cloud water vapor, or crystal water. And inside this contour, there's moist air, occasionally having some precipitation colored from green to yellow and red. And sometimes this precipitating area is located in the heart of the moist tropics, but sometimes the precipitation develops near the tropical margin rather than the center of the tropics, like here and here. And Brian that interested in the physics behind this kind of the convection developing near the tropical margin. This is another snapshot which shows some interesting features in terms of the tropical margin. And this is a little busy figure, but this blue arrows basically show the lower tropospheric motion winds. And the blue contour is the same as before, it's a 48 millimeter water vapor contour. And along this tropical margin contour, you can see in this particular case, red colored portion which shows the enhancement of the Lagrangian moisture tendency, which means that the moist air coming from the subtropics into the tropical air, there is some rapid moistening when this air comes through this tropical margin. It's a little bit hard to see in this inset figure, but basically along this tropical margin, there is some enhancement of cloud cover as well from this visible imagery. So it looks like in this particular case, there is some enhancement in the convection near the tropical margin rather than the center of the tropics. And this is from observations, but the similar things can be found in the simulation as well. So this particular example is from the idealized simulations under the radiative convective equilibrium simulations. And from the paper by the Winberg and Hoeniger, published 2 years ago. This is the simulation at near the final stage, showing some aggregated convection right here. The left panel is a fairly big moist patch that appeared at the end of this simulation. The right panel is a precipitation. And if you look closely, the peak of the precipitation is not really located at the center of this moist patch, but rather what precipitation seems to prefer near the edge of the moist patch. And that property is more evident in this vertical cross-section from the same snapshot at some line intersecting this moist patch. And this vertical cross-section shows that there's a low level of convergence, which colored yellow. This is produced by the expanding a super cold pore, which is collided with the air coming from outside, and the right on this low level convergence, huge the convection develops, which makes this intensification of the convection. So in these simulations, a theory behind it is that the multiple cold pore colliding together produce the strong convergence that eventually makes a deep convection at the edge of the moist patch rather than the center of it. And so let me get back to this ITCZ picture. And so my question is that whether we could find the similar edge intensification of convection for the ITCZ in the real atmosphere as well. And as far as you look at the climatological map of the ITCZ, it's hard to see any trace of edge intensification because the precipitation is basically occurs right in the middle of this ITCZ. But if you take a look at some snapshots of the ITCZ on instantaneous basis, sometimes you can see fairly nice cases of the edge intensification of convection. In this particular case, there is a narrow Eastern Pacific ITCZ, and a convection, which is a red, occurs close to the northern edge of this ITCZ, the band of ITCZ. This is just another snapshot. In this particular case, the convective enhancement occurs in the southern edge of the Eastern Pacific ITCZ. And if you keep looking for similar signatures, of course, it doesn't happen always, but from time to time, you come across the occasions of this kind of edge intensification of convection rather than at the center of ITCZ like this. There's another example in the almost eastern edge of the ITCZ. Yeah, this is just another example. So it looks like the edge intensification of convection occurs more often than just a coincidence. So I thought there should be some reason for this kind of intensification of convection close to the margin of ITCZ, having some, this is not just unusual cases, but perhaps there's a good reason for this. So I decided to look for what gives rise to this kind of intensification in the real atmosphere. So in this talk, I just want to show the data analysis to look into the mechanisms behind the intensification of convection at edges. And the analysis strategy here is to extract the statistical properties of different cases of convection and ITCZ. I apply a composite analysis to make some statistical features behind this, and they try to understand the underlying physics based on the morphostatic energy analysis applied to it. And the data I'm going to use here is some series of satellite data sets from the A-train instruments, like the Aqua satellite AMSR-E, which is a microwave iodometer, which is used for the previous figures I showed, actually, which is good for observing the water vapor, precipitation, as well as the some turbulent flux at the surface using some bulk formula. And also, the Aqua CERES data are used for delineating some radiative cooling, radiative heating features associated with the ITCZ. And the CCCM, it stands for the CloudSat, Calypso, CERES, and MODIS, which is 4 instruments in the A-train constellation. And combining those 4 instruments, these data sets gives you a very nice vertical profile of the radiative cooling associated with clouds and all other atmospheric emissions and absorption, as well as the vertical profile of cloud cover from the CloudSat and Calypso measurements. And these are all satellite measurements, but in addition to them, L5 analysis data are used for analyzing the morphostatic energy profiles, as well as the wind field associated with the development of convection in the Eastern Pacific ITCZ. So now let me explain briefly the compositing method for this study. The detection of ITCZ is sort of automated to make a statistical analysis, and I try to make the analysis method as simple as possible. And I decided to define ITCZ just simply as the area with water vapor larger than 50 millimeter. So that actually, this is sort of a physical basis for this, which is explored in one of my recent papers written with Barry Mipps last year. And based on some satellite-based budget analysis, the as I showed earlier, this column water vapor 48 millimeter is a nice boundary between topics and subtopics, and I just round the number to 50 millimeter in this particular work I'm going to show today. And so basically it's a green color is below 50 millimeter, and the blue color is above 50. So the boundary between blue and green portion is the boundary of the ITCZ in this particular definition. And I separate ITCZ based on the width of the meridional band. And in the several figures I'm going to show in the next slides, I'm going to explain the 4 different versions from the very narrow ITCZ up to a broad ITCZ up to the width of the 100 kilometer, from the narrow one as narrow as 400 kilometer. Because I thought the different width of ITCZ might have different physics behind it, so I didn't want to mix them all together. And the study area is just the Eastern Pacific, and the latitude is bound into the tropical latitudes. The other important aspect of the compositing method is that there are 3 different categories depending on where convection occurs inside the ITCZ. So these 3 different cases are being considered: the south edge intensification and the center intensification and the north intensification. This shows just an example for each category. And the south edge case is defined as the meridional peak of a precipitation is located within 100 kilometers of the southern edge of ITCZ. And the center case is just plus minus 50 kilometers about right in the middle of ITCZ that way. So this is also another simple way to define the location of the convection inside the ITCZ. So all the composite plots I'm going to show in the coming slides, and will show the different composites for depending on the south, center, and north intensification. So first, I'm going to show the histogram, just a histogram of the number of events that are thrown into the composite analysis into each different case. And the different colors from the left to right shows a different width of the ITCZ. The left one is the narrowest, and the rightmost ones are the broadest ITCZ. And overall, these are 3 different bars in the same category. It's a south, center, and north cases. And for every composite with different width, basically they show the similar results, except for the total number. The center cases are most frequent compared to the edge cases, but at the same time, the edge intensification cases are not so rare. So the not that different, more than twice, I think. So even though the edge intensification cases are not as frequent as the center intensification events, still the edge intensification is far from rare. So I think it's worth attention for the composite analysis I'm going to show. I just want to check the clock. So before moving on to the more deeper analysis, just let me show you the self-consistency check for the composite analysis with precipitation. So a separated composite based on precipitation is just a consistency check for the width of ITCZ, and I plot the composite precipitation. And by design, the precipitation peaks right on the center of its 0. This is the 0 distance is defined relative to the ITCZ center in this particular case. And if the 3 different cases of center, north, south are plotted together, you find something like this. And for the edge intensification cases, the distance 0 is defined at the edge. So the other peaks are supposed to be right on 0. But if you look closely, the edge intensification cases precipitation peak is not precisely on the edge, but slightly shifted toward inside the ITCZ, which is probably normal because even though there's edge intensification occurs, it prefers slightly inward, so the slightly more moist regions rather than right on the edge. But still, by construction, it's within 100 kilometers within the edge, so it's still very close to the margin between the ITCZ, inside ITCZ and outside. This is another consistency check I wanted to make sure is right, because this shows a composite moisture convergence constructed from the error 5 moisture and wind field. And I plotted this because my definition of ITCZ is pretty simple based on the current water vapor threshold. So you might wonder that such a simple identification of ITCZ may or may not be corresponding to the dynamically based ITCZ. And so this plot basically shows, if you look at, if you focus on the south edge intensification case, the width of the positive moisture convergence, which is probably well reflects the dynamically defined ITCZ. The width of this positive moisture convergence pretty well agrees with the predefined width of ITCZ here and here. So in the last case, it's basically the width of that ITCZ is dynamically 1,000 kilometers, so just as it's supposed to be. So I think the simply defined ITCZ based on moisture seems like a pretty good predictor of the dynamically based ITCZ definition. So that encourages me to move forward with this particular composite. And from now on, I just focus on this particular width of ITCZ because the other composite with different width of ITCZ seems similar. Of course, there's a difference in magnitude, but qualitatively, there's no significant difference between the width of ITCZ. So just I show this particular example with a width between 600 and 800 kilometers as a representative case. All right, so we're now ready to move on to the MSE, most specific energy budget analysis. This is a vertically integrated MSE balance budget equation, and with the horizontal advection term here and vertical MSE advection, as well as diabatic forcing terms, which consists of the surface turbulent flux here and the column radiative heating. And intuitively, perhaps you could imagine something like this about the physical ingredient of this balance equation. This is just a kettle, the boiled water inside a kettle with a heat beneath. And there's a turbulence in the water in the kettle, which is basically convection in the atmosphere. And the heat beneath the kettle is a diabatic forcing, the turbulent flux, and the column water, column radiative heating. And the energy consumed by the turbulence inside the boiled water maybe a good proxy of the vertical MSE advection, just a physical intuition. So the first, let me focus on this diabatic forcing term for each composite of the ITCZ. And this is the center intensification cases, and I plot the total diabatic forcing in the shaded colors, as well as its breakdown into the column radiative heating in this blue curve, as well as the latent heating in the yellow. And the sensible heat is basically very small compared to other terms in the tropical ocean, over tropical oceans. So I just put a constant small number to sensible heat. And basically, the diabatic forcing is a competition between the latent heat flux and the column radiative heating. But there's a strong modulation here. And because of this strong suppression of the radiative heating, radiative cooling, there is a positive peak in the total diabatic forcing. So at the center of ITCZ, there is an actual input of energy from the diabatic forcing, as you might expect. On the other hand, if you compare this with the H intensification cases, this positive peak is much smaller. The north H intensification events, there's some small but visible peak, but in the southern H intensification, there's some very visible peak, but basically the positive peak is hardly exists, so at least it's much smaller in magnitude compared to the center intensification cases. So that's something you might expect for the dynamics in the ITCZ. But question is that, so how the convection could intensify at H if the diabatic forcing is so small? So this is a question we should address. Before moving on to that, I just want to show you that what modulates the radiative cooling, radiative cooling. This is a vertical profile of the net cloud radiative effect estimated from the CERES, the CCSM products, as explained. There's a striking peak, heating peak here in the center intensification cases at high level, which is obviously the cloud long wave heating by high clouds. So basically this strong suppression in radiative cooling near the center of ITCZ is primarily brought about by this high cloud radiative effect. It is basically the greenhouse effect. And in southern and north edge intensification cases, there's some high clouds, of course, but the magnitude is smaller than the center cases. This is cloud fraction from the same CCSM products, and I just wanted to make sure that the relation between the cloud fraction and the dynamics, which is omega, the large scale vertical motion for era 5 products. And at the center cases, there's very nice deep ascent here, which is correspond to the high level cloud development. Compared to the center cases, however, the southern and north edge intensification cases, the deep peak is much weaker. The shallow ascent peak is more striking. So the shallow peak exists everywhere, even in the center, but there's some difference in the depth of the vertical ascent. That makes quite different dynamic features between the center and edge cases. There is some weak but discernible feature in the low level clouds right here, which is barely visible. But there should be some shallow convection which corresponds to the shallow ascent in the ITCZ. So now we can move on to look at this vertical MSE advection. And for showing the vertical advection, it's convenient to decompose the vertical mode into the deep mode and the shallow modes, and applied some Fulton-Schubert type vertical mode decomposition technique to separate the deep mode from shallow modes. And in this case, a shallow mode is defined as a second to fourth vertical modes combined together to best represent the very confined shallow peaks, because the Eastern Pacific is known as shallow overturning circulation. And so this is a similar composite as I showed before, but for the omega profiles as well as the deep modes and shallow modes plotted separately in terms of the color shades. What you can see here is just same as before. Under the center intensification case, there is a very developed deep convection, but at the edge intensification cases, the shallow mode dominates the deep modes, and mostly the shallow ascent seems to account for the dynamics at edge intensification cases. So, so what is the difference between the deep and the shallow modes in terms of the MSE budget considerations? And this is the same schematic as I showed before, originally drawn by the Sandin and Bonnie's paper. And interestingly, so this is the H between the ITCZ and subtopics. And Sandrine seems to be aware of some cumulative congested clouds in between, even as if she had known that there's edge intensification right there, even though this paper was written 5 years ago. But anyway, so this type of a shallow convection seems to be a key ingredient to explain the dynamics in the convection at edge. So before explaining that, I think it is useful for some of you who are not already familiar with the topical dynamics. So this briefly explains the difference between the bottom heavy ascent and top heavy ascent and its thermodynamic consequences. And the schematic was taken from the Cooney and the Larissa's paper some years ago. It's a pretty nice schematic to explain the characteristics of these different types of ascent. And the left panel shows the typical MSE profile in the tropical atmosphere. And for this bottom heavy ascent like this, which is dominated by the shallow mode, the convergence occurs very close to the surface and the divergence occurs above. And the combination of these two resulted in the MSE import because the level of the convergence MSE is rather higher because it's close to the surface, but the level of divergence is in the middle troposphere having a much lower MSE. So comparing these two imported, the converged MSE brought in the column and the MSE brought out of the column, the difference is import of the MSE into the entire column of interest. On the other hand, the top heavy ascent, which is dominated by deep mode, the convergence occurs at the minimum of the MSE. On the other hand, the outflow occurs at much higher level, which is higher in MSE. So in this particular case, it's the opposite. The MSE is exported from the column. So basically, the bottom heavy ascent is unstable in terms of the moist convective dynamics, but the top heavy ascent is stable because it's basically has a negative feedback on the column. So keeping this in mind, this shows the composite curves of the vertical advection of MSE, where it's a vertical mode decomposition into deep and shallow modes for the center case. The total advection is color, and right at the center of the ITCZ, the total vertical advection almost vanishes because of the cancellation between the negative deep mode and the positive shallow modes. So the export and versus import are entirely canceled out. But there's some positive feature near the edges, which can be clearly shown in the edge composite as well. At edges, there's a shallow mode, which is more conspicuous compared to the deep mode. So because of the weakness of the deep mode, the edge intensification cases has a more striking peak of the MSE import due to the vertical advection. So this is important aspect of the edge intensification cases. But of course, there's not only vertical advection, but horizontal advection as well. So we have to consider both the vertical advection, horizontal components of the advection. And this is the composite showing both. And the total, the vertical plus horizontal is plotted in terms of the color shade. And the different curves are individual components of this meridional and the zonal component. And the other center intensification cases, there's a very consistent negative meridional advection. So which is basically overcome the positive component, if any, in the vertical advection. So that makes the total advection fairly weak compared to the edge intensification cases. Both in the southern and the northern edge intensification, it's very clear and sharp peak in the total advection, which gives rise, it's brought about by the vertical advection, but combining the horizontal advection terms, it's the resultant total advection is a very sharp peak that is quite important to destabilize the edge thermodynamics and makes the convection develop intensely at the ITCZ edges. And but at first, when I thought these plots for the first time, I was a little puzzled because I was expecting that the horizontal advection is more negative at edges compared to the ITCZ center, because the ITCZ edge is flanked by the dry air in the subtopics, and the advection from the moisture from the dry air would result in a fairly large negative horizontal advection. But on the other hand, the ITCZ center, there's a broad region of a moist air. So my first expectation was just the opposite. The edge would have a larger negative horizontal advection compared to the center, but the result seems to be just the opposite. At the ITCZ center, there's a more conspicuous negative horizontal meridional advection. So to understand these interesting results, we could look at the vertical structure of the breakdown of the meridional MSE advection. So this plot shows the contour of the meridional wind, as well as the meridional gradient of the most static energy. So this is a product of these two basically accounts for the meridional advection of most static energy. And as you might expect, there's other center cases, there's moist air in the middle and the dry cases at the both end. So there's strong gradient in between the dry and moist air, and the opposite side on the both sides of the center. And as well as there is a striking inward flow on both sides of ITCZ in the boundary layer. But the important feature in this figure is that there is a returning flow just immediately above the boundary layer, the lower free troposphere, which is represented by the typical Eastern Pacific dynamic feature, which is known for its very shallow overturning circulation. And even though this boundary layer inflow carries a very dry air from the subtropics into the ITCZ, this returning flow does the exactly opposite. It carries a moist air from the center of ITCZ to the edge of the ITCZ. So the edge is dried in the boundary layer, but moistened just above the boundary. So if you vertically integrate the whole thing, these two competing factors cancel out, and resulting fairly a small value of the horizontal advection. But right at the center of ITCZ, there's no moistening because the center is most moist portion of the ITCZ. The only thing that the center of the ITCZ feels is that drying in the boundary layer inflow from both sides of ITCZ. So that's why the center experiences negative ITCZ and more larger negative compared to the edge of the ITCZ. Actually, that explains the features in both the edge intensification cases and the southern edge and north edge both has this inflow in the boundary layer and returning flow. This thanks for the moistening of the returning flow, the horizontal advection is not so drying at edges compared to the center. All right, I think I went through most of the important things I wanted to talk today. These are just summary of take-home messages from the talk today. The edge intensification cases are statistically not as frequent as the center intensification, but still it's far from rare. So the you have pretty much a pretty good chance to observe the intensification convection at edge if you look for patiently for the signatures. And when the convection peaks at the ITCZ center, which is probably the normal cases you would expect, the diabatic forcing has a strong peak at the center, which is caused by the suppressed radiative cooling due to high cloud along with heating. And on the other hand, the total MSA advection is negative. So the whole energy input from the diabatic forcing is quickly consumed by the deep convective mode in the vertical advection. So this is basically the most acidic energy balance that is realized at the center of the CZ. These feature characteristics in the MSA balance is very different when you look at the edges of the ITCZ. At edges, a positive peak of the diabatic forcing, which is driven flux and radiative cooling, is present but very weak compared to the other cases. But on the other hand, the shallow mode vertical advection, which is typical of the edge of the ITCZ, results in a net import of the MSE on the edges. And probably this is the factor that allows an edge intensification of convection to occur despite the weak diabatic forcing. So basically, so this is different types of MSE energy balance take place between the difference between the center and edges of ITCZ explain both the ITCZ intensification either that occurs either at the center or the edges. Okay, so this is pretty much everything that I have to talk today. But just in a few minutes, let me go through some outstanding issues that I'm trying to resolve in the hopefully in the coming months, the coming year. The first thing is a regionality, because I just focused on the Eastern Pacific, and you might wonder that the same thing could happen in other tropical regions, or maybe may not. And basically, I already looked at the composite plots in the other tropical regions, like the Western Pacific and Atlantic Oceans. And what I found is that similar mechanisms are at work, basically, but there are some differences in individual MSE energy budget terms. So I think I should look more closely into the way the different terms in the energy budget balance each other out in different regions in the topics. Also, as I introduced in my introductory part of this talk, the previous study by Windmiller and Hoeneger, based on the idealized simulation, they concluded that the edge intensification in their simulations are brought about by the supercold pool. This is different from the current idea that I came up with for explaining the observations in the ITCZ. Those two hypotheses are not necessarily mutually exclusive, so both things could happen at the same time. But maybe these things should be tested against observations as well. Although it's not easy to look for the signals of cloud pools from observations, because the cloud pools are too small and too limited in spatially that can be clearly detected from satellites or whatever observational means. And finally, I just defined the edge and center intensification cases as different entities independent from each other. But perhaps the edge intensification could be related to the center intensification, because the possibly convection at the edge could move into the center during the life cycle of convection, and those two things could be connected with each other. This is most difficult things to make look into from the observations, because the polar orbital satellites are not really good for looking for signals in rapidly changing phenomena over time. So this I have to come up with some good way to look for the signature of a changing convection from the edges toward the center. But there should be very interesting aspects of the ATCZ convection. So I try to look for the signature as well in my future studies. So that's pretty much what I have. And thank you again for your joining the colloquium this early morning. So,
thank you,
yeah.
Hiro. I'd like to open the floor up to questions. So usually we have a little bit of time where we give students to ask questions first, in case anybody has questions. Looks like there's lots of applause going on. So you can either feel free to just talk or raise your hand if you have a question for Hiro. Juliet?
Hi, Hiro. Thank you so much for this talk. It was really, really neat seeing all these, just the analysis that you can do with these observations. I'm wondering if geostationary observations would be useful at all for looking at the evolution. I imagine that might be a little bit difficult trying to get any information about like the moist static energy budgets from geostationary, but yeah, just wondering your thoughts.
Yes, absolutely. Geostationary observations are very useful for looking into the high resolution, high temporal resolution, particularly fit aspects of this kind of convective developments. And the downside of the geostationary measurements is, of course, the only available information from geostationary satellites are infrared and visible radiances, and the geostationary measurements actually don't really look through precipitation directly, and the vertical profile of precipitation, like as I showed for the cloud vertical profile or radiative cooling vertical profile, it would be difficult to estimate from the geostationary satellite measurements. But that being said, I think the geostationary measurements are one of the things I have in mind for the next step, because perhaps the combination of this geostationary information with the polar orbiting information might give us some useful clue for understanding the quickly evolving aspects of convection somewhat. So I think there's no obvious way to do so, but I think geostationary observations are absolutely useful for going to look at more temporary, quickly varying component of this ITCZ convection.
Great, thanks.
Okay, I got a note that there's a question from the YouTube stream that Pete can ask.
Yeah, Scott Lindstrom asks, can the same ITCZ analysis be extended to the SPCZ, the South Pacific Convergence Zone? He asks in the context of the development of Cyclone Vicky over the Samoan Islands in February of 2020, along the southern edge of the SPCZ. And he's wondering if knowing that the bottom heavy ascent domination could somehow help a forecaster anticipate the development of that cyclone.
Yes, absolutely. The same technique could be applied to the SPCZ as well. And yeah, thank you for the suggesting that interesting example for the application to SPCZ. And yeah, I think I haven't really thought about the applying the SPCZ because I didn't know the good example for the edge intensification for SPCZ, because SPCZ is basically much broader than the Eastern Pacific ITCZ, and I thought the precipitation the inside the most part of SPCZ is more prevailing. But yeah, if as I suggested, the cyclone development near the edge of SPCZ, and if there's such cases that occur from time to time, I think there'll be absolutely a very interesting topic to look at. So yes, it's absolutely possible, and it should be an interesting topic.
Thanks.
Any other student questions? I guess we can open it up to the floor in general. I actually have a quick question. So you argued that these edge intensification cases are associated with shallow circulations. Mechanistically, why do you think there are shallow circulations near the edges?
Well,
like I understand the evidence. Yeah, sorry.
It's a fundamental question for which I don't have clear answer for now. And that's one thing that I have in mind is that it's related to the movement of the parcel from the edge toward the center. Because if you think about returning the motion of the Hadley cell from subtopics back into the topics, probably you could think about the air column that's starting with mostly clear with non-precipitating air, which gradually picks up moisture from the warming ocean if you track the load of air coming from north to the equator. And when such air arrives at the edge of ITCZ, perhaps it begins to have the first hint of the triggered convection, and that should be some shallow one. And eventually, this shallow convection develops as a result of the moisture import that I explained. But when the convection intensifies from shallow into the deep one, the air column should further move into the center of the ITCZ. And so if you combine the movement, the meridional movement of the air from the subtopics into center of the ITCZ through the edge of it, perhaps the shallow at the edge and the deep at the center might be interpreted as the sort of the life cycle of the convection, starting from the shallow convection into the deep. So that's one image that I have to explain the Eulerian pattern of the shallow versus deep in terms of the Lagrangian movement of the air. And that's, yeah, that's one scenario that I could come up with.
Thank you. You have any other questions? No more questions? Well, if there's no more questions, then I think let's thank Hiro for a great talk and some great Q&A as well. And thank you all for attending this talk at this unusual hour. It was good to see a reasonably sizable audience. So thank you all. And thank you to Hiro
Thank you
again.
very much. Yeah, thank you.